I think we're getting started just a minute or two late today, but this is the 14th video, and I would have started on time. Melissa got me talking in class, so it's all her fault. And having said that, I know there's a homework assignment due today, and so in honor of that one being due, here's another one.
So what do we do next week?
You know, I think that maybe we'll make it due on Monday the following week. Give a little bit more time.
That will be our last Monday before our spring break. I think.
Listen, I just didn't know if you had nothing to do, so I wrote that up for you.
You should have given it to us on Monday, so it would be a birthday present for Jonathan.
Jonathan, you having a birthday?
I do. On Monday, I turn 21.
Congratulations.
So that means that I will be bringing a bottle of water to class.
I'm glad. Will you put something in it?
I can't tell you that information.
Thank you very much. All right, so homework 3 has been passed out, and I will give those to others of you that aren't here through it being posted on Blackboard. So it will also be posted on Blackboard. There is a homework due today, but before I take it up, I want to give you one more chance to ask questions if you have something you'd like to ask about. It's okay? Yes.
Number 4, I just want to make sure that we were just supposed to give a straight answer. Do we have to prove any of the
No.
answers? Or why
You don't have to prove. They're 1 point, just what are the female and
Okay.
supreme,
All right.
if,
I'm gonna make sure.
if they exist. So I'm sorry if I didn't make that clear beforehand, but that's what I'm looking for. Anybody else with a question, comment? Okay, well, I'll take up the homework at the end of the class period. Let's go ahead and start then where we left off. And that was, we had a definition. And it had to do with boundedness. So here's what it said. It said, a sequence. Let's give it some symbolism. X and N is said to be bounded. A bounded sequence. If there exists a positive number m, so m greater than 0, such that the absolute value of x of n will be less than or equal to m, and that's true for all n elements of the natural numbers. So each term of the sequence has to be less than or equal to this m inside absolute value. And so here we had said some examples last time, but I'd like to formally write out some. So the first example is if I look at 1 over n, as n runs from 1 to infinity, this is a bounded sequence. And the reason it's a bounded sequence is I can produce an m such that the absolute value of 1 over n is always less than or equal to c. In particular, I could take 1. All the terms of this sequence inside absolute values, that's going to be less than or equal to 1 for every natural number. So I can take 1. I also want to point out that that sequence is one we've studied a little bit. It's a sequence that converges. Another example is minus 1 to the n. That's also a sequence we've looked at. This is bounded, again, as it's bounded by 1. The absolute value of minus 1 to the n is going to be less than or equal to 1 for all n elements of the natural number. So each term in this sequence inside absolute value is 1. But and this sequence diverges. So boundedness, being bounded, does not imply convergence, okay? You can be bounded and converged, you can be bounded and diverged, okay? So that's something. And here's another example. If I look at the sequence n, the sequence 1, 2, 3, 4, 5. This is unbounded. This is really the set of natural numbers. We know that's unbounded. Is that okay with everybody? And so I know this is unbounded sequence. And this happens to be a sequence which diverges. Okay? It doesn't go to a particular number. Okay? I'm just saying that. But we have this theorem that we left off with. So these examples were things that I had maybe said, but didn't write down. But I have written down this theorem. It says, if x sub n is a convergent sequence, then x sub n is bounded. And we want to prove that. Now, Audra, just because it's a bounded sequence, just because you give me a bounded sequence, doesn't mean it converges. But if it converges, it is bounded. That's what we're saying.
Otherwise, it'd be an if and only.
That's right. That's right. Okay, so we want to do the proofs. Before I do the proof, let me come over here to the side and kind of give the idea. So I'll come way over here for a second. And the idea is the following. If you converge, the sequence converges something, we're going to say x, okay? So this is kind of a pictorial idea. So converge to x. To converge to x means that if I put some epsilon region about x, epsilon, some distance about x, eventually, all the terms of the sequence are going to be in here after k, after the k spot. And before that, x sub 1 could be here, x sub 2 could be here, x sub 3 could be here, x sub 4 could be here, and you have only a finitely many number of terms before k, which are really close to x. And so when you look at all these terms together, when you look at not adding, just as a set, there's going to be some, if you will, interval about 0 that's going to contain all the terms. You just make a big enough region about it. Okay? The reason is because there's just a finite number of terms that aren't controlled by here. The finite number of terms got to be some places. Okay? They can't go off to infinity in just finite terms. Is that okay? Or minus infinity. So that's why it's got to be bounded. That's the idea. And so if that's the idea, let us see how we symbolize it. Okay? You know, one of you who's in this room came to see me in my office hours to talk about a problem that's on homework 2. And it was the first problem, I think. And they said, oh my gosh, when I draw it, it's so easy to see what it is that the statement is. That was the problem with if x is sandwiched in between a and b, and y is sandwiched between a and b, then the distance between x and y, that's the absolute value between x and y, is going to be less than the distance between b and a. And it's so clear, but writing it up may take a little work. Okay? So how do we write this idea, this particular idea? Well, here's what we do. So we're ready to do the proof. So here we're going to let x sub n be a convergent sequence. First of all, in the kind of the simplest level, when we say that a sequence converges, that means it converges to a number. Okay, so there's some number which it converges to. Say x sub n converges to x. Now, here's what I'm thinking. I'm thinking that the definition of convergence can be used. And maybe I get something out of thinking of that. What am I trying to get? I'm trying to get an M. I want an M. So let me write down what we want. We need an M that's greater than 0 such that the absolute value of x of n is less than or equal to m, and that's true for all n element natural numbers, for all terms of the sequence we have. That's what I'm looking for, to show that the sequence is bounded. Okay? Well, here's what I'm going to do. I'm going to say, because we know x of n converges, that what that means is no matter what distance someone gives me, normally we call that distance what in our definition for convergence? What's the distance symbol? Epsilon. So no matter what epsilon is given to me, there's a spot in the sequence. There's a spot. What's that spot called? Okay. Such that from that spot on, all the terms of the sequence are within the distance you gave me, units of what it converges to. So here, x. Okay. So it doesn't matter what epsilon you give me, I can find a spot. Now, the spot I find depends on epsilon. Okay? The spot I have to go to in the sequence depends on what epsilon is. Yeah. Well, here I'm going to give a specific epsilon. I'm going to let epsilon be equal to 1, be given. And since x of n converges to x, then there exists a k, a spot in the sequence, this is natural numbers, such that for all n greater than or equal to k, the absolute value x of n minus x will be less than 1. That's what I got. Remember, I want to give a bound for x of n itself. Okay? For x of n itself. So as I move here, to give a bound for x of n, really we want, I'm going to write it on the side, we want x of n to be less than or equal to some m. I don't know what to choose m to be. But to get this to happen, okay, what I'm really going to have is that minus m is less than or equal to, how can I get this inequality?
X of n.
Which is less than or equal to m. That's that big fact having to do with the absolute value of A is what we called it in our big fact, being less than or equal to C. Remember that theorem? Okay. So that's what I want to get to. So I want to get x of n sandwiched in between a positive value and its negative. That's what I'm looking to do. Okay? And that's based on, that's based on the absolute value of A less than or equal to C. It means it was an if and only if. A is less than C, but yet bigger than minus C. So that's kind of what I'm working on. Okay, so I want to say something about x of n. Well, right now, from the previous statement, what I can say is, so for all n bigger than or equal to k, minus 1 is less than x of n minus x, which is less than 1. Is that okay with everybody? And all I'm doing is using this previous theorem about absolute values. I'm applying it, so I'm applying this theorem to exactly here. Okay? So what was inside absolute values is sandwiched in between the positive value and the negative value of 1. Well, I want to solve for x of n, so I'm going to add x to both sides. So for all n bigger than or equal to k, this says minus 1 plus x is less than x of n, which is less than 1 plus x. So I'm just adding x to both sides. Now remember, my goal is to get some number such that x of n is less than that number and bigger than or equal to, minus that number. The number I'm looking for is what kind of number? M had one stipulation, one characteristic. What was it? What was it? M had to be? It had to be greater than 0, okay? Well, right now, I've got 1 plus x over here. I haven't quite got its opposite over there. But, well, the first question that I would have is, look, I want an m, I want something positive. 1 plus x may not be positive. X could be a huge minus number. So, really, I need something positive. So I need to replace this with something bigger that I need it to be bigger. So if I get something bigger than this, I know x of n is smaller than n. Okay? So I'd like to get something bigger here. And then I want to produce something here smaller than this that I know is negative. Is that okay? It's really the opposite of that bigger positive thing I'm going to find. Well, I can tell you as a fact, one of the things that we learned about, it was in the same theorem that we had this one. This theorem had 4 parts to it, okay? And one of the parts was this. It was that the minus the absolute value of A is less than or equal to A, which is less than or equal to the absolute value of A. That was one fact we had. Okay? Is that okay with everybody? And so, in essence, when I compare x as my A, I can replace x with something bigger, which is at least something bigger than or equal to. Say it again. And that's right. And I can replace this with something smaller, which is minus the absolute value of x. So, for all n bigger than or equal to k, we have minus 1 minus the absolute value of x is less than x of n, which is less than 1 plus the absolute value of x.
Now, if we factor out the -1.
Yes, I guess to be very clear there. That's right. That is a good thing to do. Yes, Corey. So here what I want to tell you, though, is that we definitely have this compound inequality from what's above and this fact here. And that what I did was I replaced 1 plus x with 1 plus the absolute value of x, where this guy, 1 plus the absolute value of x, was bigger than 1 plus x. So I replaced it with something bigger. I replaced this guy with something smaller. And then, Corey, I think what you said is a good thing to write down for clarity. Okay. So, Melissa, we're in perfect position to use this fact. What I have is something sandwiched in between a number and it's negative. So what can I say from this fact? Let's see, can you give me something I can say? But that would be right here, from here to there. So here, this fact doesn't have absolute values in it, does it? This fact does, above. So what would I be taking the absolute value of? And first of all, let me write down this part, because this is when it applies. So for all n bigger than or equal to k, how do I go from here to some statement about absolute value? What's playing the role of A in my problem? That's right. So when I go up here, the absolute value of x of n will be less than or equal to, what's playing the role of C?
1 plus the absolute value of x.
Is that okay? That's what it is. It's a matching game, everybody. Okay, I don't need to say anything derogatory. I'm trying to say something encouraging. It may not sound like it, but I'm trying to. Okay? This to me is a matching game. It's like Sesame Street. Sesame Street. I'm matching. What's the same? Is that okay? That's what I'm doing. And so it's not hard. That's what I mean to say. That if we look at it and give ourselves time, it doesn't mean we get it instantmatically. That's a famous word from Rocky, the boxing movie. Instantmatically. We're not going to get it instantmatically. But we can get it, okay? So it doesn't take very long to get it. Look, somebody can say, this is my M, but it's not right. The reason it shouldn't be my M is that I'm looking for an M that bounds the absolute value of x of n, not for all n's bigger than some spot, but for all n's. Is that okay? So this is a good start. I bounded most of the terms of the sequence. The ones I haven't bounded, I don't know anything about the absolute value of x of 1. I don't know anything about the absolute value of x of 2. Is that okay? I know after k, all of them are bounded by that number. Is that okay? So how do we handle bounding those other guys? Well, here's the common process. It's what's involved in this proof. Since there's only finite numbers that are before this guy, here's what we can write. We let m equal to the maximum, the biggest value of these finite numbers. That's the value of x of 1. That's the value of x of 2. all the way up to the absolute value of x of k minus 1. And then for x of k itself, and beyond, those are going to be bounded by 1 plus the absolute value of x. So let m be the biggest number involved in that collection. There's only a finite number of them. Then, for all n elements of the natural number, x of n inside absolute value will be less than or equal to n. That's the end. But I want to explain that as we go. Okay, Chuck, here's what I'm thinking. Why can I go from this step to this step? Okay, so let's check out some of the numbers. If I want to say absolute, if I want to compare the absolute value of x of 1 to m, I want to compare that. So Megan, the absolute value of x of 1. Why is it less than or equal to m? Well, the absolute value of x of 1 is one of these numbers here. And m is the maximum of those values. If the absolute value of x of 1 is the max, then here, the absolute value of x of 1 is equal to m. Is that okay? That makes it less than or equal to. If the absolute value of x of 1 is not the max, then it's some number bigger than it. And so the absolute value of x of 1 is less than the maximum of these numbers. Is that okay? So that's why it works for x of 1. But that argument for x of 1 is going to work up to x of k minus 1. It's going to be the exact same argument. What about if I give something that's x of k or bigger? Let's say I look at x of k plus 3. Why is the absolute value of x of k plus 3 going to be less than or equal to n? Well, x of k plus 3 is bounded by 1 plus the absolute value of x. So the absolute value of x of k plus 3 is less than this guy, less than or equal to this guy. And this guy is one of the numbers that we're picking the maximum out of. So the maximum has to be bigger than or equal to this guy. Is that okay? So m is bigger than or equal to this, and this is bigger than or equal to the absolute value of x of k plus 3. So all the numbers that we could pick are going to fall into one of those two categories. They're all going to be bounded by m inside absolute values. Is that okay? That's the way it works. So that's great. Okay, just to emphasize it, Audrey, not all bounded sequences are convergent. Just to state that, so we don't get confused. All right, well, the next thing I want to turn to is some algebraic combinations of sequences. Algebraic combinations of sequences. Algebra. These are like operations on sequences. Operating. That's like what we can do between numbers. What can we do between numbers? What can we do between numbers? What kind of operations can we do between numbers?
Add them, subtract them, multiply them.
That's what we're going to do between sequences. We're going to add, subtract, multiply, and divide them. Because sequences are nothing more than numbers, or list of numbers, ordered list of numbers. So here, let's look at that. So let me get some definitions. So given two sequences, let's call them x of n and y sub n. Okay. Then I'm making these definitions. X of n plus y sub n, in addition to these two sequences. What we mean by that is we mean the sequence, the result is x of n plus y sub n. So you add the corresponding terms together, and that's what's producing the new sequence. 2, x of n minus y sub n, well, that's equal to x of n minus y sub n. 3, you could have x of n times y sub n. And that's the appropriate thing, is x sub n times y sub n for each term of the sequence. Fourthly, we could have x sub n divided by y sub n. We're going to find that as the sequence that is x sub n over y sub n as n runs from 1 to infinity. Provided, well, it's one thing we've got to be careful of when we do a division.
Y sub n is not 0.
Y sub n is different for 0 for all n element of natural numbers. Okay.
So if we have more than two sequences, do we get to keep our commutative and associativeness, or?
Yes, that happens. That is correct. It depends on what we're doing between things, yes, but that's right. For the first three, definitely, yes.
Do the sequences have to belong to the same number, same, like, real numbers or natural numbers?
Yes. Well, first of all, when we say a sequence, the way we've written it down, what we're thinking of is that they're an infinite sequence, okay? And the domain is a set of natural numbers. So if I do a quick example here on the side, just to make sure we got everything that we want. Look, I'm going to do something that's not quick for me, just because of kind of what you asked, okay? So as an example, I'm going to give 3. Let's look at x sub n is equal to cosine of n times pi over 4. It's n runs from 1 to y sub n is equal to let's say sine of n pi over 4. Let's say w sub n, so we'll get some more, n running from 1 to infinity. Let's say that's equal to 1 over n. And let's say that z sub n is a sequence. Let's let that be equal to n itself. Okay, then what is x sub n plus y sub n? Well, it's equal to those two things added together. So it's each individual term of the sequences added together. That's what it is. And so just to do something with that, so just to do something with it, to list some of the terms, when n is 1, what do I get? I get cosine of pi over 4. What is that? That's square root of 2 over 2, isn't it? 1 over square root of 2. Plus sine of pi over 4, isn't that the square root of 2 over 2? So don't I get really the square root of 2? Isn't that right? The first term is the square root of 2. So although it's a real number, but boy, it's an irrational number. It's not a nice number, but that's what I get. It doesn't have to be nice. What happens when n is equal to 2? It's cosine of pi over 2. What's cosine of pi over 2? 0 plus sine of pi over 2, which is 1. What's the next term? That's when we're looking at 3 pi over 2. So cosine of 3 pi over 2, 3 pi over 4, I said the wrong thing. Cosine of 3 pi over 4, let's see, that's going to be minus square root of 2 over 2. And sine of 3 pi over 4, that's going to be positive square root of 2 over 2. So we get 0. And so it keeps going like that. Let's see, what happens when I let n be equal to 4? It's cosine of pi, that's minus 1. And sine of pi, what's that? 0, so I get minus 1. What else? I mean, we've got a bunch of other ones. I'll list one more. So what if I look 5 pi over 4? That's minus square root of 2 over 2 for cosine of it. Sine of 5 pi over 4 is also minus square root of 2 over 2. So I get minus square root of 2. Is that okay with everybody? And it keeps going. So that's what we're getting as the sequence when we add them together. Is that okay with everybody? You just add each term for n. Okay, let me do a little bit more here. Extend this. So here, what if I looked at what's, let's say, what is W sub n times Z sub n, for my example? Wouldn't that be 1 over n times? This is a sequence that's always 1. Now that's really nice to see. What happened here is we took a convergent sequence, 1 over n. We multiplied it by a divergent sequence, n. You know why n is divergent? The reason that n is divergent is because the sequence that's always n is not bounded. And if you're convergent, you have to be bounded. So if you're not bounded, you are not convergent. Bounded doesn't imply convergence. But if you're not bounded, that implies that you are divergent. Is that okay? So I took a divergent sequence and I multiplied it by a convergent sequence in this particular case, and I got something that was convergent.
Is it not always that case?
No. If I had taken this to be n squared, Zn was n squared, I'd be getting n every time, which was divergent. No, nothing can be said every time about anything that involves a divergent sequence, okay? There isn't anything that we can say. But there is something to say if everything's involved, it's convergent, okay? But before I leave this is another example. If I look at Wn over Z sub n, and I can look at this because Z sub n is always n, it's never 0. This is really, and I guess the way that I should have written this, I didn't write it the right way, was this. This would be 1 over n divided by n, which is really equal to 1 over n squared. These terms will be 1 over 1, 1 4, 1 9, and so forth, 1/16, forever. So those are some examples. I didn't do the subtraction one, but you can do that. All right, here's a big theorem. And let me go ahead and write it on the other board because it's a little bit lengthy. It's got several parts to it. I probably could have fit it in there, but anyway. Here's a big theorem, and as I was saying, if we're talking about convergent sequences, so I'm going to let x sub n and y sub n be two convergent sequences. first statement is, I'll write it this way, the sequence x sub n plus y sub n converges, is convergent. And not only that, the limit, whatever it converges to, as n goes to infinity, of x sub n plus y sub n equals to the limit as n goes to infinity of x sub n plus the limit as n goes to infinity of y sub n. 2. I can say the same thing for each one of these algebraic combinations of convergent sequences. So x sub n minus y sub n converges, where what it converges to, so the limit as n goes to infinity of x sub n minus y sub n is equal to the limit as n goes to infinity of x sub n minus the limit as n goes to infinity of y sub n. 3. X sub n times y sub n. What does it do? Well, if x sub n is convergent, y sub n is convergent, the multiplication is convergent. Where the limit as n goes to infinity of x sub n over y sub n equals to the limit as n goes to infinity of x sub n times the limit as n goes to infinity of y sub n. And finally, if y sub n is different from 0 for all n element natural numbers, and the limit as n goes to infinity of y sub n is different from 0, then the limit as n goes, x sub n over y sub n converges and the limit as n goes to infinity of x sub n over y sub n equals to the limit as n goes to infinity of x sub n over the limit as n goes to infinity of the y sub n's. That's the theorem.
So it's kind of using our 4 definitions to say that when we're taking 2 convergent sequences, that applying these operations will
Results in a convergent sequence. And not only will it result in a convergent sequence, but what the resulting sequence will converge to is either the addition, subtraction, or the multiplication, or division of the limits of the original sequence. So the way that we would say this, Corey, is that the limit of a sum of sequence is the sum of the limits of each individual sequences. That's what we would say. So mathematicians are quick to say this, hey, the limit of the sum is the sum of the limits. That's kind of the phraseology we use. Well, I think I have time to at least do one of them. So proof. So Chuck, we got 4 parts. So the setup's the same for all 4 parts except for the last one. We'll get a few other things. But I'm going to say let x sub n. Look, it's convergent. Okay. So if it's convergent, then that means it converges to something. Is that okay? So let x sub n converge to what should we call it? What do you converge to?
L1.
I'm going to do what I was told, but I was hoping for a different answer. Did anybody know what I was thinking? X. And I was going to say let y sub n converge to y, because they'd be related, you know. Now we got L1. I'm not going to put L1. No, we're going to be very suggestive in what we say. And let y sub n. I'm not so sure he didn't do that on purpose. He could have, I'm telling you. Converge to y. Probably did. Be a troublemaker, I'm telling you.
Why don't we make the second one be Z?
because then it's easy to get confused. It's confusing enough. So let's try to make it as easy as we can to relate objects to each other. Okay, for part one, we want to show that the limit as n goes to infinity of x sub n plus y sub n equals to x plus y. That's what we want to show. Because the limit of x sub n is x, and the limit of y sub n is y. That's what we want to show. How do I prove that a sequence converges to a specific number? How do all those proofs start? Audra, how do all the proofs start when we're trying to show some convergence? That's exactly what I want. So that's kind of the template. So let epsilon be greater than 0 be given. And Chuck, what's the next phrase that I'm going to use? We need a... Okay. That's right. That's a spot. It's a natural number. It's a spot in the sequence. Such that for all n bigger than or equal to k, the absolute value of the quantity x of n plus y sub n minus the quantity x minus y will be less than the epsilon that was given to me.
X plus y.
That's exactly right. Big mistake on my part. Good, John. Should be x plus y. That's what we're saying converges to. Very good. Okay, that's what I want to have happen. And what I know is that x of n converges to x. That's right, John. And y sub n converges to y. So look, if this x of n is getting really close to x and y sub n is getting really close to y, then when you add them up, they ought to be getting really close to x plus y, whatever number that is. And that's the kind of the idea that it makes sense. And so how do we show it? Here's what we show it. We'd say, well, note, so I want to make this guy be less than epsilon. So here's what I note. We note that the guy that I want to be less than epsilon, if I fiddle with it algebraically, I can rewrite this as x sub n minus x, and I'm not going to show any associativity, any multiplication by minus 1. I'm just saying, I know I can rewrite this as x sub n minus x plus y sub n minus y. They're the same things. Now, here's something that happens a lot in analysis. Look, we're trying to show this thing is less than. We're trying to show an inequality, less than something. Okay? And so what we'll do is we'll say, well, I know that the thing that we're trying to show is small, less than something. I know it's less than this other guy. And if I can show this other guy is less than epsilon, I got what I want. Is that okay with everybody? So here, I'm thinking this. This is one quantity. We can think of it as one quantity, one number. And we think of this as just one number. And so really, inside absolute values, we've got one guy plus another guy. So I'm thinking I got A plus B. And I'm telling you, I would like to say that's less than epsilon, less than or equal to epsilon. But intermediate step, I would say it's less than something else. What's the absolute value of A plus B less than?
Absolute value of A plus absolute value.
And that is called something.
Triangle.
That's what it's called. So here's what the triangle equality says. It's a big fact. It's something we're going to use a lot. Here's the first time we're really using it. This guy then is going to be less than or equal to, what's my first object? What's A?
X of n minus x.
Plus the absolute value of y sub n minus y. Now look, I want this guy to be small. Is that okay? This whole thing to be small. Less than epsilon, right? Well, if you want something to be less than epsilon, what if you make this be less than half epsilon? And you let this be less than, make this be less than half epsilon. So when you add them together, you'd be less than epsilon. Is that okay? So how can I make this be less than epsilon over 2? Well, wait a minute. I know x sub n converges to x. So I can make the absolute value of x sub n minus x be as small as I want by pushing far enough along in the sequence. And from that point on, whatever point I pick that's far enough along, all the terms will be really close to x. And so I'm going to write this down next. We got time. I don't know what time it is. Does anybody know what time it is?
1:44.
That's a song lyrics from a song by Chicago from the 70s. That's what I was quoting. Does anybody even know what time it is? Does anybody even care at all? You can look it up, you can Google it. Okay, it's on YouTube, it's a song about Chicago, that's what I was doing. I sing to myself when I'm up here, it's sad. Half the time it's Michael Jackson songs. Most often it's Live It Off the Wall. I'm living on the wall, and that's why I'm singing that song. Anyway, I'm glad you know that now. Since x of n converges to x, or since x of n converges to x, I can make the absolute value of x of n minus x be as small as I want by pushing far enough along the sequence. How small do I want it to be?
Less than epsilon over 2.
Less than epsilon over 2. There exists, I'm going to say, a case of one element of the natural numbers. I'm using the definition of convergence, okay? Such that for all n bigger than or equal to case of 1, the absolute value of x of n minus x is going to be less than epsilon over 2. Remember what I write here have to have one characteristic. What I write here has to be a positive number. That's the characteristic. The epsilon has to be positive. I'm going to say the same statement, Megan, except I'm not going to say it for x of n's, I'm going to say it for, that's right, I'm going to say it for y sub n's. So, Corey, if this converges to y, then there exists, I'm not going to say case of 1, because it might not be the same spot.
Case of 2.
All right, case of 2, element natural number. Better to say case of 2 and some other number like m or something like that. We kind of get them related. Such that for all n bigger than or equal to case of 2, y sub n minus y is going to be less than epsilon over 2. Okay, wait a minute, there's a trouble spot here, Chuck. A little bit of a trouble spot, something that can be easily overlooked. I've got kind of what I want here. I got kind of what I want here. But they're not happening necessarily at the same spot. So to make sure that they're both happening, I have to do something we've done before in this class. I don't know if you remember. But I'm going to pick one k. What's the k I want to pick? The biggest one. And the way we're going to ensure that is we're going to say let k equal to the... That's exactly what we're going to do. Outstanding. Okay? What time do we have? You didn't care, but he keeps asking.
149.
Okay. So I'm real close to what I want. I'm in the way. It's hard to see. Okay. So, for all n bigger than or equal to k, we have the two things I need. X of n minus x is less than epsilon over 2, and absolute value of y sub n minus y is less than epsilon over 2. So, for all n bigger than or equal to k, the thing that I was looking at, x of n plus y sub n minus x plus y, that quantity. Remember, this is the guy we want to be less than epsilon, that's right. Is less than or equal to the absolute value of x of n minus x plus the y sub n minus y by the triangle equality. But each one of these, for n's bigger than or equal to k, are less than epsilon over 2 plus epsilon over 2, which equals to, summarizing, so for all n bigger than or equal to k, here's what we have, x of n plus y sub n minus x plus y inside absolute value is less than epsilon. It's less than this quantity, which is epsilon. Okay? Thus, x of n plus y sub n, what does it converge to? Okay? That is the proof of part 1, and that's a good spot for us to stop at. I'm going to tell you the part 2 with the subtraction works the same way. I mean, the exact same way. I'm going to do it. But it's the exact proof. Same thing. For multiplication, not the same. Okay? For division, not the same. It's each other even. It's harder. Okay? Division is the hardest one. Okay? So multiplication, you have to kind of introduce something. Division, you got to kind of come up with a couple of facts in between to help us out. We'll look at those next time, okay? All right. Look, one more thing before we shut it down that I want everybody to know. We're on page 65, and I'm trying to, well, really we're on page 64. We're on page 64. When I get through with page 66, that's the material for our first exam, okay? But we're going to have this homework due Monday. I won't grade it. I'm thinking our next exam won't be next week. I'm thinking it's going to be the week after that on the Friday.
So last Friday before spring break. I think that is. Or
No, I think that's a little.
week.
I think we got a week for
There's a
it.
week or two. There's a week or two this week.
Yeah, I think we got some time. Okay, I think we'll be.
It'll be the 20th.
I'm ready for spring break too, but it's not that
I was
close.
keeping up on this fast.
So anyway, I'm going to give you a study guide, and I want to say this thing. Sometimes I think teachers are a little shy. I don't know why to say this. It's almost like there's a negative connotation associated with what I'm about to say. But I mean what I'm about to say. If you don't know the definitions, we can't do very much. Okay? So you got to be able to quote the definitions. So if somebody says, well, how do you know that? And you say, well, I memorized it. Well, that's something to do. So you need to be able to state those definitions. Don't be shy to say, I'm going to memorize this. Okay? There's nothing wrong with that. And then from that, we can say, what does that mean? If you don't know what it says, you can't figure out what it means. Does that make sense? So memorizing it is a good thing. All right, anyway, that's all I got for you. Let me shut this